Welcome everybody to our second talk of the day. Our second talk is going to be Daniel Vahla, preparing for free threaded Python world. Can we have applause for Daniel?
All right. Hello, everyone. Welcome to PyCon 2025. I am so happy to be able to present here after such a long break of PyCons in Finland. Today, we're going to go through how to prepare for a free threaded Python world, because the Python is going in that direction. The GIL will be disabled eventually by default. And to prepare to live in this world, I think we should have a recap on thread safety and synchronization primitives. A little bit about me. Name's Daniel Vahla. I'm a consultant at Maverick Software. Have been working with Python for about 7 years. Generally, I'm interested more into the cloud and serverless, but I've been executing it so far in Python. Additionally, I'm an organizer for Helsinki Python Meetup and PyData Helsinki as well. So why does this talk matter? Python 3.14 ships now with an opt-in version of a GIL-free build that you can execute with the Python 3.14t mark. And with GIL disabled, you achieve true parallelism, which means that whatever GIL has been protecting you from, you will not guarantee that safety anymore. So you will achieve real race conditions that would have been covering by GIL to run your code safely, even though it wasn't really safe to begin with. So to protect ourselves, there are 7 synchronization primitives that we should know about. So what was GIL as protecting us from was that there have been operations that were working just safe under the GIL, like read and modify statements, assignments to a dictionary, or anything around just working with reading an assignment. Now, without GIL, you need explicitly synchronize your threads so that the operations will behave in a way that you expect them to. Now, to exemplify all of these scenarios and the ways to protect ourselves, I have prepared for us an example, which will be a dice game. The rules of the games are pretty simple, is that there will be a one game object and a one dice that needs to be shared between the threads. The threads are representing our players, and the rules of the game themselves is that we roll the dice to accumulate score, and if a score for a single player goes over 20, that player wins. And each demo builds on top of the previous one. There will be some comments saying that we have been reusing some code inexplicitly. So maybe let's start with the baseline, which is what happens when we don't synchronize, so our race condition. Problem is that we will be sharing state between the threads that will be not protected. Therefore, the result of accessing that state will be non-deterministic, which means if you run this example a couple times, you might get different results. The updates in between the threads are lost, and in the end, the state is corrupted, the data is corrupted. So let's have a look. We have our dice object, which initializes to 0 value, and our roll method that will be basically rolling the dice, which is just throwing a random in from 1 to 6. Then there's our game class, which initializes a single dice. There's a couple print statements to show us where we are at. And then there's the situation that when we are under the score of 20, we should continue to roll the dice and keep assigning the score. Once we have escaped the condition, we eventually will say that the player has finished. And how do we run the code? Usual statement that if the name's main, so we can execute it from the script. We initialize the game, we initialize 3 threads, and we assign them just player names, just player 1, 2, 3, append them, start them, and eventually join them to get the results. So please do tell me if this is readable from your distance, or should I zoom in some more? Plenty readable. All right. So we can see from the statements that the dice has been rolled 3 times, each time by each thread, but the score that the players have assigned to themselves ended up being the one that were the last roll. So not really what we wanted to achieve in our mind with the game, but we can see clearly this is a problem. So unpredictable behavior, if we would run it again, we might get even the second roll achieved. So data is possibly corrected, not deterministic results. So it's clearly visible now that the problem is that we are sharing the dice without any protection. So first solution, lock, also known as mutex or mutual exclusion. What it does is that it blocks any threads for accessing it, except for passing the one that holds it. Others will have to then wait until it's released. And the general purpose is that it will protect the sections of our code that we want to share between the threads, so that our mutable state that is shared in between will be protected, and all of the operations on it will be behaving as we are expecting it to. So let's take a look. What have we changed? Now in the dice, we have added a lock. And we are saying now, whenever you want to roll, you should acquire the lock. So then whenever the thread that is playing the play method will be trying to roll the dice, it will be getting to the line where it says with self-lock, which is the context management way of acquiring the lock. The lock object has also methods called acquire and release that you can call manually, but it's much better to call it with a context manager style, so that you won't have to worry about acquiring and release, because that is more error prone. We will run it just the same way. There has been no updates to this part of the code, but I like to keep it here so I remember to jump to the code. All right. What happens now? We can see that whenever there's the dice roll, the player is achieving the score, and it's actually assigned to each one of the players that have rolled the dice. The logs might be a little bit out of order, but the score that was supposed to be achieved by the player is accurately assigned when rolling the dice. So you can see that we are consistently achieving the assignment of the value of the dice to the player. There is no data corruption because we are protected by the lock, and we achieve what we wanted to do, which is the thread safe dice rolling. But there's some other scenarios that we would like to think about that other objects might be useful for. For instance, reentrant lock is a lock that will allow you to acquire itself more than once from the very same thread. Because if you would like to acquire again a lock that you have already acquired within your thread, you will achieve a deadlock situation where you cannot proceed further with your code. So, reentrant lock saves us from that problem. It allows multiple times to be acquired by the same thread. It internally keeps a stack of how deep does the recursion level go. And we need to release the same number of times that we have acquired it. So that's why instead of running the acquire and release methods, I strongly suggest to just keep adding the with statements or just use a recursion. And the recursion is the one that we are achieving here. We can see that not much has changed. We just changed the type of the lock, and we just added an extra rule to the dice that if we have rolled a 6, we can just recursively call the roll method so that we are once again running into the statement that says that with self-lock. Thanks to it being a reentrant lock, this will now not achieve a deadlock. We will proceed forward. The rest of the game stays as is. There has been no updates, so we can clear and run it here. And maybe a bit more scores rolled, but yes. With that, we can see that whenever the dice rolls a 6, there will be another roll to achieve, and therefore the player will get a little bit higher score, so eventually he will get to 20 and finish the game. So yeah, easy way to do recursion with locks. If you have a reentrant lock, no deadlocks achieved on reentry, and if we have this nice rule in that 6 can roll again, then this is the very simple way to achieve it, that it will be running just fine. Now, on to the next one, the semaphore. Semaphore is a lock that also has a count within it. So if we have to think about that, how many resources or how many threads do we want to allow to access? If it is more than one, then we should have something that counts it. So a semaphore allows specific amount of threads to access the block, and whenever each one enters the with statement or you run the acquire method, you decrease the count that you have created when creating the semaphore, and release will increment it. Useful cases for that is, for example, a connection pool, like databases are optimized for up to, for example, 30 connections being running against them. So if you have a backend running, it will be useful to have a semaphore there so that only 30 threads can achieve connection to the database so we don't overrun it. The resource limits, so max concurrent users, like if you have a specific rule that in here we will achieve that only a specific amount of players can be allowed to play at the same time, then this is the synchronization primitive to use. And otherwise rate limiting, like if you believe that we should have like a global configuration on our backend, that if we have a REST API and we would like to limit how many threads we are running for handling the API calls, then we can achieve it also with a semaphore. So now I'm skipping a little bit from the code. The imports and the dice class will remain the same as in the demo 1. So it's just a simple lock and rolling methods, and the imports are just implicitly whatever we need to have. In our game, we will now say that we will allow at most 2 players at the same time to play. And we achieve that by then creating the semaphore and saying that it is the max players. Now to play the game, we say that we need to acquire the semaphore, which will let us then let in the thread if it is still within the limit, then continue with the rolling, and at the end of finishing the game, we should just release the semaphore. Now, setup for running, just slightly a little bit different, that we add the parameter for how many max players we have. So this is 2, and we will continue with 3 threads. So the third one should have to wait. All right, so if we run the semaphore, I added a little bit of a timeout here so you can see more clear that when each one is running the game and which one is waiting. So the player 3 has to wait to join. Players 1 and 2 are happily running their game, and when player 2 has achieved a score of 20 and left the game, the player 3 was allowed to join and continue with his turn on the game. So yeah, as we can observe, just like we wanted, only 2 players were allowed in at the same time, others had to wait, and it's first in, first out ordering, and quite simple solution. But it can be bug prone, because whenever you release the semaphore, you increase the count, and if your code is a little bit more complicated and it has release statements in a couple of places, and you might end up releasing more than once, then you will basically have a condition that you will continue increasing it and allowing more and more threads to access your resources, which was not what you planned in the first place. The basic semaphore will decrease to 0 and then hold, but it can increase infinitely. A bounded semaphore will throw an error when you try to release more times than what it had been created with. And the error that it throws is the value error. So the best practice, as for me, is to always use the bounded semaphore. This is something that people would like to probably discuss a little bit more, that do we really need for performance always a bounded semaphore, but I would say that it's so negligent loss of performance that just use a bounded semaphore and protect yourself from the bugs. So same situation as before, we just updated our semaphore into a bounded semaphore, and we keep acquiring and releasing as we were before. I couldn't think of a good way to introduce a bug in here, so I have just forcefully added it at the end of our game. So we are at the end of our game trying to release the semaphore one more time, and if it would succeed, it would have printed as an error, and otherwise it will throw an error, which is the value error, and then we will achieve the print of the bug being caught that we try to release beyond the capacity. So running our bounded semaphore, we can see that it behaves just exactly the same as our first one, but when we try to release at the end of the game one more time, the bug has been caught, we try to release it beyond capacity, and we don't have to worry about it anymore. So it's just a special edge case for a semaphore to take care of. If you want to have peace of mind, just use the bounded semaphore. So the game works exactly the same. If it tries to release one more time than it was supposed to, we throw a value error, which we can then catch and protect ourselves from. Following up, event, also known just as a simple signal. What it does is simply set a Boolean value true or false. When it's initialized, it's false. Then threads can wait for the event to flag itself as true. One of the threads will set the value to wake up the other ones. And the use cases. So we can, for example, start multiple threads at the same time, or start part of the processing at the same time if everyone is waiting for the condition. We can signal that now it's time to shut down the processing, or any sort of one-time notifications that need to happen across all of the threads running. So how are we going to achieve that? We will add to our game an event that we will just say that it's our start event. So in our play method, we will now wait until the event has been set. And the way that we're going to achieve it is that once all of our threads have been created, I'll add a little bit sleep statements, then only then we can run the game. So I will print the go. That means that all of the threads have been created and they are waiting for execution, and game starts. So let's take a look at the demo. We could see the threads have run 1, 2, 3, and then they had to wait for half a second before the event was launched. So we have the go statement, then all of the players continue to start the game, keep rolling the dice, and eventually finish. Simple synchronization can be used for many other cases, but that is the one I presented for this demo. All players have waited for the start signal. One set wakes all of them that have been waiting for it, and we achieve a synchronized start. What if we want to do something a little bit more complicated? We would like to have a condition so that we just don't want to set a flag true or false, but we want to wait for something to be achieved that we have some logic behind. So just like any other more complicated synchronization primitive, they are all built on the log, so they can achieve the acquire release statements, and we can also use it in a context. We have the notify and notify all methods that will allow notifying either specific amount of threads. Notify by default notifies just one thread. You can also pass a specific number, or notify all if you just want to wake up everyone. But a specific note here that I added is that it's best to use it in a while loop, because the notify and notify all is not the only way that the log can be released. There may be also some system level events or even timeouts or anything of the sorts that can wake up. So then we would like to still rerun the condition, because it might be so that we have been woke up, but the condition was still not met. So the use cases where to use it: if you have a producer and consumer, then we would like the consumers to wait and the producer is ready. So there's some condition for that. If you have some otherwise complex state changes, and just generally we are waiting under a specific condition. So here our example is a little bit longer. We will have our condition, and condition for this example is that if enough players have joined, then we can start the game. It's similar to the previous one, but this time we explicitly tell that we want to just wait for everyone to join. So the condition object itself doesn't actually hold the logic for your statement that you want to hold on, but you just want to say that there is a specific logic that we would like to wait for, and if it has been met, then a thread or the main thread will notify everyone that it's time to continue with the code. We run the game similarly, that we just say that the number of players that we would like to have is 3 before we can continue with the execution. Get some water. So as we have seen from the code, the players have announced that they've been added. So we are counting them 1, 2, 3, and then the call is being made to say that the condition has been met, notify everyone that was waiting so they can start playing the game. They start rolling the dice and they finish playing. So each player did increment the counter, and then when the counter achieved the number that, or the condition that we have set for ourselves, then all 3 were ready so we could start the game, and the last player that had added itself to the counter and noticed that the condition was met called the notify all. And down to the final demo, the barrier, which allows us for an n-way synchronization. We created with a count of how many threads do we want to make so that they will wait at the barrier, and then when all of them have been met at the barrier, you can think of it like a start line. If the line is full, they will all go in at the same time. The threads can call wait to wait for the barrier let it through, and the none will proceed until all of them have arrived. And I also added one extra thing that I'd like everyone to know, that the barrier also has an optional callback, which is being executed the moment all of the threads have arrived, but before any of them have started the execution. I thought that this is a really cool thing about the barrier, because it allows for specific side effects that we would like to achieve, just to notice that everyone has arrived at the barrier. Use cases. Multi-phase algorithms. You can think, for example, if you want to have optimization for your breadth-first search, where you have a long queue with how many objects you have to traverse on a specific level, then you can divide it between threads, and then once the queue is empty, then the threads will be waiting before they can achieve the next level of the search. The round-based games, like in our example, so we will tell that everyone needs to finish their round before we can proceed with the next one, or just in general, if you want to synchronize your computational stages in data processing or any other examples. So having a look at our code, we have the very same game as from this previous example with an extra setup that we would like to have 3 rounds and 3 players. The barrier will wait until all 3 players have been set up to wait for the barrier. And once that happens, then an action will be triggered when our action here is defined. That we will just like to say that which round are we at, and let's print it. So when we're playing the game, each player will jump into the round and we'll wait for all the other players to be at the same situation, and then we'll continue with rolling the dice and printing our score. Setup for running is also very similar. We just add the parameters to the game. All right. As we could see, the players have been set up to be ready. The round 1 started thanks to our action parameter. Then we have the scores added for each round, and eventually the 3 rounds have finished. I didn't have the condition for waiting until score of 20. I thought it was enough just to show that 3 rounds can be run in this way. So all players have been synced at the barrier. The callback, really useful thing, has printed the round start, and it was very clearly synchronized execution for our game. So to summarize all the demos we have went through and all the primitive logs that I have explained to you guys again, we have a nice table. The log, useful for mutual exclusion, just protect the shared state in the simplest of the ways. So in our examples, the dice was always protected with the log before it can be run by a separate thread. Reentrant log, in case we want to add some spice to the dice and tell that if we roll a 6, we're allowed to roll again to get some extra score. Semaphore, to limit how many threads can concurrently access this block of code. And bounded semaphore, if you want to be a little bit more defensive about running the acquire and release statements. Event, we want to simply signal that now is the time to proceed with specific block of code. Condition, when we have something more complicated and we have to wait for it to be true. Or a barrier, we want to just synchronize how many resources can arrive at a specific block before we will continue executing it all at once. So the key takeaways from this talk. Guilt-free Python is here, still in opt-in. I hope Hugo will be generous and put 3.15 as a default that it's the guilt-free. We'll see about that. Thread safety is critical. It's coming. If you have not taken care about it before, I would like to tell you that it will happen within a year or 2. This will be the default situation, and then you will just probably panic and say that, you know what, I don't need Python 3.15 or 3.16 just yet, but we'll just stay on my 3.13 for a couple of years until I have everything safe. Well, to achieve safety, you need to know your primitives. And I suggest everyone just test it. Test now, test if the behavior is the way you want it. There are some good libraries for testing your Python code against thread safety. And small tip from me, just use the bounded semaphore. The loss of performance is negligent. And when in doubt, if you don't know if your statement is safe or not to be run in a multi-threaded environment, just use the log. Just do it. All right, these slides are available at pycon2025.vahla.fi. If you'd like to read more about what has happened with the GIL, please read the PEP 703. The Python documentation for which you would like to read more about the classes and the primitive synchronization mechanism. You can read from those links. Compatibility tracker is a nice website that shows us which of the libraries are already tested and guarantee us that they can be run in a free-threaded environment. And if you really want to do a deep dive, I suggest reading the Python Concurrency with Asyncio by Matthew Fowler. That was written quite many years ago, but it gives you a better idea about how to do concurrent programming. All right. Thank you. All right. For those who want to stay, I have rewards for people who have questions and for people who have paid attention. There has been a bug sneaked in one of the demos. Can someone tell me which demo had a bug?
I think it was the second or third, I don't really remember.
Correct. The second one has been not adding the, as you can see, we had the score value now to hold the actual score of the dice when you had the double roll, but our players continued to getting the value